Good morning. This is Richard Oteng-Frimpong, and this morning I will be sharing some preliminary results from a study that we have been doing to be able to develop high throughput phenotyping protocols for peanuts in Ghana. And this has been done mostly with the assistance of Professor Maria Balota. Now, in Ghana, most of the preferred peanut traits are found within the Spanish market types, and therefore these dominate farmers' fields and are usually devastated by leaf spot diseases and occasionally granite rosette diseases. Now, some of our previous works have indicated that application of fungicides can actually help improve the yield on farmers' fields, but however, these are not usually used because of availability and sometimes the technicalities involved. And so the breeding pipeline is targeting host plant resistance as a more friendly and sustainable approach to improve the yield of peanuts. And breeding, as we know, is a game of numbers, and therefore, if we have a system that allows us to screen a large population, it will improve our chances of making progress in the breeding program. And this is where the high throughput phenotyping protocols come in. And these HTP techniques give us a lot of advantages, and they have become very popular in many programs with a lot of publication out there on it. Now, one major advantage is that it is non-invasive and also drastically removes subjectivity from the data that we collect, and also permits us to take repeated measures. And therefore, our objective was to apply a drone-based photogrammetry in granules that rely mainly on open source software to be able to estimate biomass yield and leaf spot diseases. And particularly in this instance, we wanted to compare it with the manual phenotyping that we've been doing over the years. So we selected 12 short duration Spanish type genotypes and from our larger breeding population and put them in a lattice design with 3 replications, and each replication had 4 blocks. And when the plants were at the R4 and R5 stages, we collected phenotypic data on early leaf spots and then late leaf spots, as well as the home yield at the R7 stage. Now, the early leaf spot and late leaf spot diseases were scored on a scale of 1 to 9, with 1 being highly resistant and 9 being most susceptible. Now, to make working with this data much easier, we converted it to the area under disease progress curve values, where the lower the value, the better or the more tolerant the genotype is. So briefly, what we did was that we had access to a DJI Mavic Pro drone, which we programmed with the Pix4D app on a standard iPhone, and it was set to fly at an altitude of 20 meters, and the images were captured with a 90% front overlap and then an 80% side overlap. And the camera was also set at a 90-degree angle. Now, once the images were captured from the drone, we now use them as an input file into another open source software called WebODM. Now, the one we use here is an offline open source toolkit that is mainly used for processing aerial imagery. Now, the images from the drone are, like I mentioned earlier, used as the inputs for the WebODM. And the WebODM uses the GPS coordinates embedded in the images from the drone to recreate this flight path. And then from the flight path, it generates these point clouds with a sparse matrix, which is then fine-tuned to become a dense one. And then the dense matrix is also fine-tuned to give us a standard output image like this. Now, the WebODM has several settings, but in this particular instance, for our study, we set it to work at a resolution of 1 centimeter. So The output from the WebODM then became the input for another package called the FieldImageR. Now, FieldImageR is an R package that has a compilation to analyze orthomosaic images from research fields. Now, the package has an inbuilt pipeline that allows us to crop the image, rotate it, remove the soil background, and also the weeds that may be found in the background of the images by changing some of the settings within the app. Now, the package also allows us to build a shapefile in order for us to extract the information from each specific plot. And these are some of the shapefile that came out from our analysis, and the individual plots we are now able to extract the data from the individual plots, and this is exported in the form of an Excel file that we can now use for analysis in other softwares. So the FieldImageR has several indices that could be worked on, but for this our particular studies, we focused on 3, which is the canopy cover, and the vary is the visible atmospherically resistance index, and then the normalized green-red index. So this is the interface of the WebODM, and basically, after stitching the images, it can now display them in the background of the map, an inbuilt map for us to see. And one thing is that the WebODM itself has an inbuilt plant health function that allows you to visualize the health of the plants. Now, for this image here, we selected vary as the indices, and we are able to see some of the plots with still green color and others with the red color. Now, visual scoring on the plots indicated that those plots that we see them as green here had very good tolerance or resistance levels for leaf spots as compared to the other one. So, like I mentioned earlier on, our intention is to be able to substitute our manual phenotyping of the genotypes that we are evaluating. So we were trying to compare the UAV indices with the conventional phenotyping that we did on our plots. Now, the UAV was done at different stages, different growth stages from R1 to R7, and the comparison showed that the strength of the relationship increased with the growth stage of the plants. However, with the NGRDI and the vary, the relationship became stronger earlier as compared to the canopy cover. So from that observation from the UAV indices, we decided to do a regression of the correlation point to see or to confirm this observation. And from our graphs, we were able to confirm that indeed the UAV indices and the conventional phenotyping data were much related, but most importantly, as the plant's growth, that kind of relationship becomes more evident. And this gives us an idea of at what point in time that we should be taking the data if we want to use that for our selection. So as a breeding program, we decided that, okay, so if we are to replace our conventional phenotyping with the indices from the UAV, how does it compare when it comes to selection of our best genotypes? So we built an index with the early leaf spot scores, late leaf spot scores, and then also the home yield on one side for the conventional, and then also built another index for the NGRDI, and then the vary, and then the canopy cover. Since the data showed that these relationships were better at the R7 stage, we used data at the R7 stage for this selection. And interestingly and most importantly, the genotypes that were selected was the same across, with the exception of one additional genotype that was selected as one of the best from the UAV-based indices. We believe that is probably due to the fact that the UAV-based indices took away a lot of the subjectiveness. But for us as a breeding program, what made us happy about it was that it selected the same genotypes in the same order with the first 4 for us. So in conclusion, what we are saying is that the plant health indices represented by the VARI and then NGRDI had a very strong relationship with early and late leaf spot scores from our fields, and as well as the biomass or the home yield. But then the NGRDI and the VARI were better for indicating plant health than the canopy cover. And so since the same genotypes were identified for both of them, we think that the UAV-based indices has a lot of promise that going in the future we can take advantage of. However, this is only data from the first year, and we are going to continue working on this to be able to validate these observations that we have made in our first year of evaluation. So on that note, I want to thank these organizations for their continued support to our breeding program, and to the board and organizers of APRES for giving us the opportunity to share our results. Thank you very much.
Richard, excellent. Very good presentation. Are there any questions for Richard? I guess I'll start off. Thank you for going ahead of me, because now I don't really have to present very much later. I guess one of the questions that we have is, do you have an understanding of, I guess, leaf spot percentages on the actual plots, or is this essentially more to look at the whole plot only, from a drone capture standpoint? Like, are you looking at different percentages of leaf spot infection, like the actual lesions on the plots, or is this just to focus on the whole plot as a more of a whole high throughput method? And do you think that the leaf spot percentages would change any of your ratings, I guess?
Yeah, so in this instance, what we did, the plot capture, the data that was captured from the drone perspective, that image from the different stages where the leaf spot severity was lower, the NGDRD values were higher. So that kind of negative relationship allows us to we are able to tell that, okay, this was more severe than the other. So it was not just one value for all. At the different stages, there were different NGRDI and then VARI values, and that correlated strongly negatively with the severity that we score. So when we go in manually to look at the lesions and give it a score of 1 to 9, in between that, then when you compare that to the NGDR and then also the VARI, you see that that one was higher. And when the score was the rating, the severity rating was higher, those values were also lower. So in effect, not a very straightforward quantitative value, but it gives you an idea of the level of severity. But like I said, this is just the beginning, and I'm sure by the time we get to the end of it, we would have been able to make more definitive conclusions in relation to that aspect.
Excellent. Any other questions for Richard? Not seeing any, so
we have a question in the chat, and
that's, oh, I see it. Okay.
Yep.
So from Barry Tillman says, was the H yield the same as pod yield, or was this total biomass?
No, this is total biomass from the what do you call it, at maturity. So it was just the biomass, not the pod yield.